You can't see them, you can't feel them, yet every second, billions of neutrinos pass through your body silent, invisible, and perhaps they're the ones deciding the fate of stars, the destiny of the universe itself. Chapter 1. A first encounter with the invisible. Imagine this, something is passing through your body right now, not once or twice, but billions of times every second. You can't see it, you can't feel it, you've lived your whole life unaware of its presence, and yet, it's always been here. It moves through you, the walls around you, the earth beneath your feet, like a whisper in the fabric of reality. These are neutrinos. Some call them ghost particles, and it's not hard to see why. They're incredibly small, nearly massless, and they almost never interact with anything. Trillions of them stream from the sun, fly through the planet, and keep going as if nothing existed in their path. To them, we are transparent. The story of neutrinos is one of the most fascinating and mysterious in all of physics. It's a story that begins, not with a discovery but with a problem. In the early 20th century, scientists were puzzled by a strange behavior in radioactive decay. When certain atoms broke apart, the energy released didn't add up. It seemed like something was missing. Some energy had simply disappeared. But the laws of physics don't allow that. Energy doesn't vanish. So, what was going on? In 1930, a physicist named Wolfgang Pauli offered a bold solution. He proposed that maybe there was another particle involved, so light and elusive that we couldn't detect it. He didn't have a name for it yet, and he admitted it might never be found, but he was certain it had to be there. Otherwise, the math didn't make sense. Later, Enrico Fermi gave the particle a name, neutrino, meaning little neutral one. In Italian, at first, it sounded like science fiction, a particle that doesn't carry charge, barely has mass, and passes through solid matter like a ghost. It seemed too strange to be real, and for decades, we had no way to prove it. No tool could detect something so silent, so invisible. Until one day, someone tried listening instead of looking. In 1956, deep inside a nuclear reactor in South Carolina, two scientists, Frederick Rains and Clyde Cowan, finally detected a neutrino. They didn't see it directly. Instead, they set up a giant vat of water, filled with special detectors, hoping to catch just one rare moment when a neutrino might bump into something. It was like waiting for a single snowflake to land on a hot stove and leave a mark. And incredibly, it worked. After weeks of silence, they recorded tiny flashes of light, evidence that neutrinos were real. The ghost had been caught. It was a quiet victory. The public didn't notice. There were no headlines. But in the world of physics, it was like opening a secret door into the deeper layers of reality. Since then, we've built even bigger detectors, often buried deep underground or under ice. Why underground? Because the Earth filters out everything else. Cosmic rays, background radiation. All that remains are the neutrinos, passing through in silence. One of the most famous is Supernovae in Japan, a massive tank of ultra-pure water, hidden beneath a mountain. It's lined with thousands of sensors, waiting for the rarest flicker of light, the soft footprint of a neutrino's passing. Think about that for a moment. An entire facility, built not to see the world but to see what the world ignores. It's not unlike building a cathedral to listen for silence. So what makes neutrinos so interesting? It's not just that they're hard to detect, it's that they're everywhere. They're being made in nuclear reactions, in the sun, in distant stars, in collapsing supernova, even in the radioactive decay happening inside the Earth. And yet, they barely leave a trace. In a sense, neutrinos are the universe's background hum. They're like the wind between galaxies, carrying stories from places we'll never reach. Some neutrinos hitting Earth today were born in the hearts of stars that died billions of years ago. They're time travelers, and their silence is full of meaning. But maybe the most beautiful part of this story is what it says about us. We only discovered neutrinos because someone believed in something they couldn't see, because they trusted the math and trusted the universe to make sense, even when their senses said otherwise. In a world obsessed with visibility, what trends, what shines, what makes noise, neutrinos remind us that not everything valuable is loud. Not everything that matters demands attention. Some truths are quiet, Some forces are invisible, and sometimes the most profound discoveries begin not with certainty but with curiosity. What is this invisible thing? Why can't we see it? What is it trying to tell us? These are the kinds of questions that drive science, not just to explain what is, but to reveal what could be. As we continue this journey, we'll see how neutrinos aren't just background noise. In many ways, they're central to the biggest events in the universe, from the death of stars to the shape of galaxies, from the mystery of mass to the limits of what we know. They may be small, they may be silent, but they are not insignificant. And maybe, just maybe, there's a lesson in that for all of us. If you're still here, still curious, thank you. This was just the beginning. In the next chapter, we'll follow the neutrinos into the heart of a dying star and see how something so silent can unleash the most violent force in the cosmos, a supernova. Stick around, you're going to want to hear this. Chapter 2. When a star dies, stars live for millions, sometimes billions of years. They burn quietly in the vast silence of space, fusing hydrogen into helium, shining with a light that warms planets and defines galaxies. To us, they seem eternal fixed points in the night sky. But like all things, stars also have endings, and the bigger the star, the more dramatic that ending becomes. This is not a slow fading into darkness. It is a collapse, a scream, a violent act of nature that sends shockwaves across the universe. It's called a supernova, one of the most powerful explosions known to science. And deep inside that explosion, neutrinos play a role more important than light, more critical than heat. They may be the ones who decide what happens next. So let's imagine the death of a massive star. For millions of years, the star has fused hydrogen into helium. When the hydrogen runs out, it turns helium into carbon, then carbon into oxygen, and so on. Like a layered onion, the star builds shells of heavier and heavier elements, until one day it reaches iron. Iron is different. It doesn't release energy when fused, it consumes it. So when a star starts building up iron in its core, it's writing its own death sentence. The fuel is gone. The reactions stop. Gravity takes over. The core begins to collapse under its own weight. In less than a second, a core the size of Earth shrinks to the size of a city. The pressure becomes unimaginable. Atoms are crushed. Protons and electrons combine into neutrons, and suddenly, the core becomes incredibly dense, like a giant atomic nucleus. This moment, the exact instant of collapse, is where neutrinos arrive. Inside that collapsing core, temperatures reach over 100 billion degrees. Neutrinos are created in huge numbers, trillions upon trillions of them, as particles slam into each other at extreme energies. They are formed so rapidly, in such incredible amounts, that they carry away 99% of the energy released in the collapse. Think about that. The visible explosion of a supernova, the light we see from Earth, adds just 1% of the energy involved. The rest is carried away by neutrinos, streaming outward faster than light can escape the thick outer layers of the star. And for a brief moment, the universe listens. In 1987, astronomers witnessed a supernova in a nearby galaxy. It was bright, but something else was detected too. A flash of neutrinos arriving just before the light. It was the first time humanity had heard a supernova before it was seen, and it proved something remarkable. Neutrinos escape first. They are the messengers, but their role is even deeper than that. As the neutrinos rush out from the collapsing core, they slam into the outer layers of the star. Billions pass through without effect, but a tiny fraction collide, and when enough of them do, they create a shock wave strong enough to blow the star apart. This is how the supernova happens. This is how elements are scattered into space: gold, oxygen, calcium, iron, the building blocks of planets, of life. Without neutrinos, the outer layers might never explode. The star might just collapse into a black hole, quietly. The universe would miss its grand fireworks. We might not exist at all. So when you see light from a supernova in the sky, remember, the real story isn't the explosion. The real story is what happened just before the silent burst of neutrinos that made it possible. There's a strange kind of beauty in this. In most stories, the hero is the one everyone sees, the one who shines the brightest. But in the death of stars, the true hero is almost invisible. a particle that slips through matter, through time, through everything, a whisper of energy that turns collapse into creation. It's easy to ignore what we can't see. It's easy to believe that power only belongs to what's visible. But neutrinos teach us the opposite. They are the ones who shape the ending end, the beginning. And perhaps that's the deeper truth hidden in physics. Every star we see in the night sky will one day die. Some will fade, others will explode. And in those final seconds, neutrinos will decide the outcome. They will either carry energy outward, giving birth to a supernova, or they will leave quietly, allowing the star to collapse into darkness. Creation or silence, rebirth or black hole. The choice doesn't come from what shines, it comes from what barely leaves a trace. In the next chapter, we'll come back to Earth. We'll look at how these neutrinos rain down on us constantly, where they come from, how they pass through everything, and how we've built quiet instruments to catch their silent journey. But for now, just pause for a moment. Somewhere out there, another star has just collapsed, and before its light reaches eyes, the neutrinos have already passed through. Maybe one just passed through you. Chapter 3. Earth in a neutrino rain step, outside on a quiet night. Look up. The stars seem still. The air feels calm. But in this moment right now, we're standing in the middle of an invisible storm. Every second, more than 60 billion neutrinos from the sun are passing through each square centimeter of your body. That's billions per second, per square centimeter, and not just from the sun. Some neutrinos come from deep space, from supernova, from the Big Bang itself. They've been traveling for billions of years only to pass through you in complete silence. This rain never stops. It never rests. It doesn't care about day or night, mountain or ocean, living or lifeless. It is always here. We are immersed in it, bathed in it, and yet, most people live their entire lives never knowing. Why can't we feel them? Because neutrinos interact so weakly with matter, they almost never touch anything. Out of the trillions that pass through your body, almost none ever collide with a single atom. To them, the Earth is just a thin veil of fog. Even the solid core of our planet barely slows them down. Imagine trying to shoot a bullet through a wall of steel and it goes through without making a scratch. That's how neutrinos behave. Not just once, but billions of times per second. And so, for scientists, detecting a neutrino is like trying to catch lightning in a bottle with no sound, no light, and no warning. But we tried, and we succeeded. Across the world, scientists have built enormous detectors designed to do just one thing: capture a single trace of a passing neutrino. One of the most famous is Super Kamiokande in Japan. Deep beneath a mountain, in an old zinc mine, lies a cavern filled with 50,000 tons of ultra-pure water. The walls are covered with thousands of light sensors. It looks more like a science fiction temple than a laboratory. When a neutrino happens to collide with a water molecule, and remember, this is very rare, it creates a tiny flash of blue light, a whisper of energy, a fingerprint in the dark, and the sensors, silent and waiting, catch it. These moments are precious. Each one tells us a story about the sun, about a distant galaxy, about the birth of the universe itself. Another marvel sits in Antarctica, the Ice Cube Neutrino Observatory. Here, scientists have buried thousands of detectors deep into the Antarctic ice, spread across a cubic kilometer. The ice is so clear, so undisturbed, that it becomes a perfect medium for detecting the faint glow from a neutrino's rare interaction. No noise, no light pollution, just silence and cold, waiting for messages from the stars. These detectors aren't looking at the sky the way telescopes do. They're looking through the Earth, catching neutrinos that come up from below, having traveled through the planet untouched. They allow us to map the invisible. And what are we learning from all this? We're rediscovering that the universe is full of quiet signals, and neutrinos are one of the most faithful messengers. Unlike light or charged particles, neutrinos don't get stopped or redirected. They go straight. So if we detect one, we know exactly where it came from, and we know it carried undisturbed information. It's like receiving a sealed letter from across the galaxy, untouched by wind or fire. Some of these letters are from cosmic explosions. Others are from black holes devouring matter. and some are from the earliest moments after the Big Bang, ancient neutrinos still drifting through space, carrying clues about how everything began. There's something beautiful, even poetic, in the way we study them. We build vast, sensitive instruments, not to see what's loud and bright, but to sense what is quiet and passing. We spend decades watching for moments that lasts less than a billionth of a second, and yet those moments give us knowledge that could never be found any other way. It's as if the universe has a secret language and neutrinos are one of its silent syllables. Let's pause and think about what this means. Right now, the air around your home, your city, the Earth is flooded with particles from beyond the stars. They've passed through dead galaxies, collapsed stars, and ancient explosions. Some have traveled longer than our planet has existed, and most of them we'll never notice. They come and go, undetected, forgotten. But a few leave marks, a few collide, and when they do, they remind us we are not alone in this universe. We are not separate from it. We are inside it, woven into its fabric, listening to its echoes. In the next chapter, we'll dive into a strange mystery. Even though neutrinos are nearly massless, they seem to have mass. But how much? Why do they change as they move? And what does that mean for our understanding of reality? We've built machines to catch them. We've watched them escape stars. But now we must ask, what are they truly made of? And could they be showing us a path beyond the physics we know? Chapter 4. The Unsolved Mystery. Do neutrinos have mass? In science, every answer leads to more questions. When we finally proved that neutrinos were real, when we caught their faint flashes, when we saw them escaping dying stars, it felt like a moment of clarity. But then something unexpected happened. Neutrinos started acting. Strangely. They weren't just ghost-like particles passing through space. They were changing. A neutrino born in the heart of the sun might arrive at Earth as a different kind of neutrino. It was still a neutrino, but somehow it had shifted its identity during the journey. This phenomenon is called neutrino oscillation, and it changed everything we thought we knew. Let's take a step back. There are three known types or flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. Each one is associated with a different fundamental particle. In the early days, we believed that a neutrino would stay the same type from the moment it was created to the moment it was detected. But experiments began showing otherwise. When we counted the number of neutrinos coming from the sun, something didn't add up. We were missing 2/3 of them. Where had they gone? Had the sun stopped producing them? Were our detectors broken? No. The truth was far more mysterious. The neutrinos were changing flavor mid-flight. Imagine you send out a beam of pure red light, and by the time it reaches the wall, it has become blue. That's what was happening, except with particles, not colors. The only way this kind of transformation is possible, according to quantum theory, is if neutrinos have mass, real, non-zero mass. And that was a big deal, because the standard model of particle physics, the very framework we use to describe reality, assumed neutrinos were massless. If that assumption was wrong, then maybe other parts were wrong too. It meant there were gaps in our most trusted model of the universe. Neutrinos had just opened a door into unknown physics. But how much mass do they have? That's still a mystery. Even with all our detectors, all our calculations, we can't pin down their exact mass. We only know that it's very, very small. Smaller than any other particle with mass. So small that it's still measured as less than a number, rather than a precise value. Some experiments suggest that the total mass of all three neutrino types combined is less than 0.12 electron volts. For comparison, an electron, already incredibly light, weighs about 500,000 times more than that. It's like weighing a whisper in a storm. So why does this matter? Because the presence of mass, no matter how small, has consequences. It affects how neutrinos move through the universe. It affects how galaxies form. It even affects how fast the universe expands. And if neutrinos have mass, then how they get that mass becomes a new frontier. Do they follow the same mechanism as other particles? Or is there an entirely different process at work, one we haven't discovered yet? Some physicists even wonder, are neutrinos their own Most particles have opposites. Electrons have positrons, protons have but with neutrinos, It's possible that the particle and its antiparticle are actually the same thing. If that's true, it would rewrite our understanding of matter and antimatter. It could even help explain why the universe didn't annihilate itself in the first seconds after the Big Bang. Neutrinos, in their quiet way, might hold the key to why anything exists at all, and yet they stay silent. They pass through our detectors, barely noticed. They shift and flicker in flavor, like shadows changing shape. They defy our expectations, not with explosions or noise but with quiet contradiction. This is the paradox of the neutrino. The more we learn, the more we realize how little we know. It's humbling and it's thrilling, because somewhere in that mystery, in the flicker of flavor, in the trace of mass, there might be a doorway, a path to a deeper understanding of nature, a truth beyond the standard model, a clue to the next great theory of everything. In a world so focused on what can be seen, neutrinos challenge us to pay attention to what can't. They invite us to think differently, to ask better questions, to embrace the possibility that the universe is stranger than we ever imagined and more beautiful than we ever dared to believe. In our final chapter, we'll widen the lens. We'll explore how neutrinos, these silent messengers, may have shaped the very structure of the universe, how they influence not just stars, but the fate of galaxies, and why, long after the light has faded, neutrinos may be all that remains. Join me there, one more step into the quiet unknown. Chapter 5. Ghost particles that shape the cosmos. We began this journey with something nearly invisible, tiny particles slipping through matter, through planets, through us. And now, at the end of our path, we find something unexpected. These ghostly neutrinos might shape the universe itself. It sounds impossible. They're so small, so quiet, so easy to ignore. But that's exactly what makes this discovery so extraordinary, because even silence has weight. Even the faintest presence leaves a mark. In the early moments after the Big Bang, the universe was hot, dense, and wild-filled with particles smashing into one another, space expanding at breakneck speed. Among the first to form were neutrinos. And here's the amazing part. They're still here. The cosmic neutrino background, like the cosmic microwave background, but even older still, fills all of space. These ancient particles have been traveling for nearly 14 billion years, untouched, undisturbed. They are remnants of creation, fossils of the very first second. We've never seen them directly. They are too faint, too elusive. But we know they must exist, and we believe they outnumber atoms. So how could something so small affect something as massive as the cosmic structure? Because even the tiniest particles can shape the behavior of galaxies if there are enough of them moving in the right way at the right time. As the early universe cooled, matter began to clump together, forming clouds of gas, stars, and eventually galaxies. But neutrinos didn't clump. They were too fast, too light. They slipped through the forming structures, stretching out the gravitational webs of the cosmos. In a strange way, neutrinos acted like cosmic editors, smoothing out some parts, enhancing others, balancing the fabric of space as it took shape. Without them, galaxies might have formed differently, slower, more chaotic, or maybe not at all. And it doesn't stop there. Even today, neutrinos may be affecting how fast the universe expands. In cosmology, this is called the Hubble tension, a growing disagreement between two ways of measuring the universe's rate of expansion. Some scientists think that neutrinos, or particles like neutrinos, might help resolve that tension, not by being loud or obvious, but by doing what they've always done, moving quietly, subtly adjusting the rules from behind the scenes. It's almost poetic. The universe's most delicate question might be answered by its most delicate particles. So, what does this all mean for us? It means the universe is not only shaped by what explodes, but also by what endures, not only by brightness, but also by influence. Neutrinos remind us that power doesn't always come from size or noise. Sometimes, it comes from consistency, from quiet persistence, from being everywhere, always moving, always present. And in a way, they reflect something deeply human, because we, too, are shaped by invisible forces, by thoughts we can't explain, emotions we don't see, moments that pass quietly, but change us forever. The influence of neutrinos feels familiar not because we understand it completely, but because we live with invisible influence every day. Right now, neutrinos are still flying through your body, through your home, through the earth. They carry messages from stars that died long before we were born. They may someday tell us what lies beyond the standard model, or even what lies beyond this universe. But more than that, they show us a different kind of beauty. The beauty of what's overlooked, the beauty of what whispers instead of shouts, the beauty of silence that carries meaning. As we close this journey, I invite you to take a moment, not to understand everything because some mysteries deserve time, but to feel something deeper, a sense of connection, a sense that we are not just observers in this universe, but part of its quiet story, that even the smallest thing, if persistent enough, can shape everything. If you found wonder in this invisible world, if these silent travelers sparked a new curiosity in you, leave a comment below. I'd love to hear what part of this journey stayed with you. And if you want to keep exploring stories like this, quiet ones, beautiful ones, hidden ones, there's so much more waiting to be uncovered.